Okay, so last time. Okay, so welcome back, everybody. I hope everybody had a good spring break. Nice and relaxing, I hope. Hope you got around to doing something fun. Here's the theorem that we were talking about last time, and I've made it clear I'm a big fan. This was a massive assistant to me in my undergraduate years. Huge number of integrals can be resolved much more efficiently than sort of the usual iterated integral approach by citing this theorem when it applies. Keep in mind, you need both of the conditions to apply. One of the biggest mistakes that students make here is they see that they have a symmetric domain. They get a little too excited about that, right? And they forget to even consider the possibility that the function, the integrand, might not be odd. In fact, most integrands are not odd. Right? It's a special characteristic to have to be an odd function. Likewise, also another landmine on this. Same line. You have to use the same line for both the oddness and the symmetry of the domain. Be careful with that. That said, symmetry arguments very, very powerful. And so you take, for example, this super ugly integral right here that I suppose we could try to do as an iterated integral. What a nightmare, though, that would be, especially in light of the fact that this is going to mess things up pretty badly for the outside integral, right? Yikes. But then a couple of quick observations. This integral, zero by symmetry. Extremely powerful result. Okay. And then one of the last things we talked about was what it means to give me a complete symmetry argument. And keep in mind, again, this class is not about answers, it's about ideas, it's about arguments, reasoning, right? And so the reasoning that I want to see, the documentation of your reasoning that I need are these 5 things, right? It's very important that you establish what your line of symmetry is. Right? It's really arguably the first thing that one has to do if you're going to make a symmetry argument. Over what line? Right? The reflection over that line needs to be documented because when you make a claim that your integrand is odd, you need the formula for reflection in order to be able to demonstrate that the function actually is odd. Right? And then, of course, also don't forget to note correctly, if it's, assuming it is, that the domain is symmetric as well. Again, you don't have to prove that domains are symmetric. When a domain is symmetric, it's usually pretty clear that it's symmetric. And the arguments are a distraction, I think, sort of a distraction from what the main ideas here are really fundamentally about. Okay, so this is what I want to see if you are going to make a symmetry argument, which again I encourage. Right? Give me these 5 things. Okay, heads up though, you do have to be careful. And I think this is the very last thing that I said before spring break. Be careful when you use symmetry because it's a very delicate argument. Everything has to line up just so in order for a symmetry argument to actually work. And so here's the tragic scenario that comes up that I see students doing. They'll take a question where there is no valid symmetry argument, right? For whatever reason, maybe the integrand's not odd or whatever, right? There's something goes wrong. The argument there is not there. There is no symmetry argument to be made. But the student maybe either glosses over that seemingly small point of, this one little thing I didn't check, and then is lured into writing down a symmetry argument, and that's all the work they have on their page. And the thing is, all of that work, even if most of it is actually true statements, all of that work is in the direction of a dead end. There is no symmetry argument. That is not progress toward any actual solution. You cannot solve the problem that way if there is no symmetry argument in the first place. And so it's not progress toward a solution. It's very, very difficult then for me to, as creatively and generously as I try to think up, well, in what sense could I view any of this as partial progress? For partial credit, it can be very hard for me to do. Very dangerous. When you're using a symmetry argument, be super careful. Double check everything, right? Make sure that it's actually right, because if something's wrong, then it's you're in an awkward situation. All right, so here's an example. Here's an integral, and here's an example solution that a student might submit for this integral. The domain implied by these bounds is symmetric. That's a true statement. That domain is symmetric. In fact, that domain's symmetric in multiple senses. It's arguably a good thing. But anyway, the domain is symmetric. This function has an odd symmetry. True. It does have an odd symmetry. And the student then spikes the football and says the integral is equal to 0 by symmetry. Here's the problem with this work. There's a tremendous amount of stuff that's been left out of the argument here. I claim only 2 of these 5 requirements have actually been documented in this reasoning. Right? So in fact, we can count them. It's an easy count. The student has correctly observed that the domain is symmetric. Right? The student has correctly observed that the function is odd. But this student has not said anything about what the line of symmetry is over which they're making this argument. That's not the student didn't say anything about the line of symmetry. The student did not give a formula for the reflection, and the student did not demonstrate that the function is odd. So that's arguably 60% of the work is missing. 60% of the relevant ideas, anyway, missing. So anyway, this is not a good answer to the question. Arguably moving in the right direction, but not very well documented. Does everybody see what's wrong there? Okay, moving along. Here is another example, and now this one I'm going to document thoroughly. So we've got a domain bounded by certain curves, and here's that resulting domain, this thing in here. All right, and over that weird set, what we want to do is compute this integral, which, not that bad. It's a polynomial. Integrand I'm not particularly scared of, but I do see corners, and whichever way I slice this, I'm going to be hitting not only a corner, but I'll be hitting 2 corners. So this will be 3 separate iterated integrals if we do this the old-fashioned way, right? So, rather than that, here's an idea. Look at that line right there. Notice how the domain appears to be symmetric over that line, and hopefully not hard to persuade yourself that it's actually symmetric over that line. After all, these 2 curves are clearly perpendicular to it. These 2 lines, I should say, are clearly perpendicular to it. So I appeal to your geometric intuition. These 2 blue lines are their own reflections over the green line. And then this curve here, curves, think of it as 1 or 2 to suit yourself. But the reflection of the one is the other, or it is its own reflection, however you want to say that. And again, I'm not going to write down the algebra of that. I think it's believable. I think it's intuitive. And if it's not, come talk to me about it. I'll be very happy to walk you through the reasoning of how I know algebraically that this is its own reflection. We did an example before spring break, and I'm happy to show you more if you come to my office hours or wait after class or something like that. Okay, so, all right, so notice I have indicated that this domain is symmetric. And again, notice now there is some reasoning. I gave some reasoning here as to why it's symmetric, but you're not responsible for doing any of this. So you don't have to do any of that there. I included it in the notes just as a guide for sort of communication purposes, but that's not expected for you to document in your own work. Okay. All right. So now going through our list of things that we have to write down. First of all, what is our line of symmetry? Well, our line of symmetry is that right there. Right. What is the formula for reflection over this line? If I have a point, I don't know, here, and I want to look at its reflection over here, how does that reflection work? I claim that this is the formula for that reflection. That is not immediately obvious, right? Why this is the reflection. So let me show you my rationale there. That's this discussion over here. Given a point, x comma y, keep in mind that if that's x comma y, then I can make this what I like to call a little rectangular frame here that shows what distance is x and what distance is y. And what's nice about this little rectangular frame is that even though the point itself, if I were to look at this ray coming out of the origin, this light blue, vector, it's really not clear, given that's a weird angle, it's not clear how that would reflect over the line, but it is pretty clear how this rectangular frame reflects. It reflects like that. Right? This is a 45-degree line, so a horizontal line, and I know that's 45, I know this is 45, that makes this a right angle, that makes this vertical, right? The geometry is just kind of convenient there. So I think this is a nice little hack for how to think through it. In this case, every example is different, of course, but in this case, that little frame trick is a nice hack. So our process of reflection, turning the light blue point into this purple point, you can just kind of look at the reflected rectangular frame, look at the distances, what became negative and what distances or what distances. I think it's pretty easy to persuade you that this is the formula there. How are we doing? Is everybody with me? Okay, so got our reflection. All right, let's see here. We're 3 pieces in, right? We've documented the line, the formula for the reflection. I've claimed the domain is symmetric. Now I'm going to make the claim that the function is odd, which is a 4th bullet point. But again, it only works, you only get credit for saying the function is odd if it actually is. Right? So I'm going to give myself a check mark even though we haven't actually confirmed it yet. Now let's confirm that the function actually is odd. Keep in mind how we confirm a function is odd. Let's go back to the formula. Here we go, the definition. A function is odd if when you plug in the reflection, that causes a minus sign in the value of the function. Okay? This is what it means for a function to be odd over a certain line. So reflection in, minus sign out. So let's play the game. Looking at this example here. Oh, and I need to zoom out again. Okay, so I've got to take this formula for the reflection, put it into my function, right? And see what the function turns into. So specifically then, I need to do this right here. Right? Notice I'm plugging in the formula for the reflection, plugging it in to what goes into the function f. Here's our function f. And now introduces an awkward little moment. I got to plug in negative y comma negative x into my function, and what's awkward is that my integrand, my allegedly odd function is written in terms of x's and y's. My reflection is written in terms of x's and y's, and that's going to seem a little bit weird. One way to deal with this is just to remember, as you're plugging this in, the thing that's where x is supposed to go, that's what you plug in for x. So this, this x right here becomes minus y. This x right here becomes minus y. So you can think of it like that. Admittedly, a little confusing. In fact, really, this is a kind of a confusion of variables. So there's an easy way around this. If you're not comfortable with what I've done here, very reasonable. If you're not comfortable with it, then here's a workaround. You can rewrite your reflection just in terms of different dummy variables. So for example, I can rewrite this as r of just, I don't know, s comma t. And I would just make it negative t comma negative s. Right? And take that. Take this and plug it in. In other words, use that for the reflection. Everything would be in terms of s's and t's, and then there's no confusion of variables. Yeah.
Wait, is the role of finding the reflection to show that it's odd?
That's one of the things that you're gonna. That's what you're gonna be doing with it is demonstrating the oddness of the function. Yeah.
Okay. Like that's what I would.
Think of it as sort of a two-step process. The way you prove something is odd is step one, you identify exactly what your reflection is, and step two, then you check the resulting algebra when you plug it in. Yeah.
Okay.
Yep. Is that satisfying? I'm not sure if I answered your question.
Yeah, I think I'm just trying to understand the context of like why we're doing the reflection.
Yeah. Just to give you a crisp and short answer, the reason I need this reflection is because I need something to plug into the function to confirm that I get a minus sign. Mm-hmm. Yeah, that's right. Okay, is everybody happy? Okay, so so this rewriting the reflection in terms of s's and t's is a nice little hack if you find the plugging in either confusing or risky. If you don't trust yourself to get that right. Okay. That said, then you just have to follow through the algebra, and this algebra is no big deal. I mean, there's various minus signs to keep track of, and what happens when you raise a minus one to what power, and et cetera, et cetera. Again, don't play too fast and loose with the algebra. Everything's delicate, right? If anything goes wrong and you get a yes when you should have had a no, crash and burn, landmine, catastrophe, right? So don't be in a hurry on that. All right. But it did work out. Plugging in the reflection does give us a minus sign. Function is therefore odd. We've demonstrated it. We've done all 5 of our requirements. Integral is 0 by symmetry. We drop the pen and walk away. All done. This integral, we don't have to slice it into 3 separate pieces, thus giving me 3 iterated integrals, which would be tedious and annoying. Okay. Yep.
I had a question about the previous example when we had the domain bound by 0, 1, and 0, 1.
Yeah.
So instead of always saying a line L where D is symmetric over, could you make a triangle argument instead? Because for this example we have 0, 1, 0, 1, so then you just have a symmetry around a shared hypotenuse. So would you need to specifically argue I have this line, or kind of say symmetry visible with this hypotenuse?
You need to give me the actual line. Now you're correct that this is a square here, and the line of symmetry that we're going to use here is, now we have a lot of choices from the point of view of the domain itself, right? But the line of symmetry that actually makes the argument work is this one. That's correct. So you got to give me the line. You then need to give me a formula for how you reflect over that line, because that formula is how you would prove that the function has this claim to odd symmetry. And then, there's your 5 steps. Okay. Yep. Is that what you were asking?
Yeah.
Okay. Cool. All right. So, moving along. Here's another example, and this is a landmine example. And I include this landmine example because, this is natural. This is going to come up. You're going to see this kind of thing. Starting by looking at the domain. Even before we draw a picture, we see a triangle. We see that the corners, I see some good stuff in these numbers here. The 1 and the minus 1 are negatives of each other. I love that. All right, that's encouraging. I see a lot of zeros. It's a good sign. In fact, not only do these numbers kind of look suspiciously symmetric, this triangle is symmetric. True statement. T is symmetric. The integrand here, that integrand is odd. It does have an odd symmetry. And this is a very strong temptation then. And again, so you have to, resist the urge to see a symmetric domain with an odd integrand and to just, run for the daylight at the end of the tunnel, and then you step on the landmine. Right? Because even though we have both symmetry of the integrand and symmetry of the domain, they're over different axes, different lines. And over the y-axis, the function is not odd. Over the x-axis, the domain's not symmetric. So there is no symmetry argument here at all. No possibility for a symmetry argument. So any discussions, in your work about a symmetry argument in relation to this example question isn't going in a valid direction. So again, very, very dangerous. Does everybody see what the risk is here? Okay. All right. So for one thing, super careful, double check everything. There's another sort of a nice side effect of insisting that you go through all 5 of the steps. Because as you're going through all 5 of the steps, you have to explicitly choose a line and explicitly write down the reflection. And then when you try to explicitly demonstrate the oddness, well, then you're just gonna see that no, it doesn't work. Okay. Is everybody okay with this example? All right. Okay, 3 dimensions. This is super analogous. It's the same thing. The main difference in 3 dimensions is that we don't reflect over lines, we reflect through planes. Frankly, this is the most relatable sort of a reflection. Anytime you look in a mirror, right? The mirror is the plane, the reflection is the person looking back at you in the mirror. Right? That's exactly our primary intuitive notion of a reflection. Okay. And with that said, we have the exact same notion of oddness, namely that a reflection in gives you a minus sign out. We have the same notion of what it means for a domain to be symmetric. It is its own reflection, or, said equivalently in any number of different ways. And we have the exact same result. You'll notice I've laid it out on the page to look exactly the same. In fact, if I had to guess, I'll bet you that I literally did a copy-paste from several pages back and then just, changed a couple little micro details. So it's through a plane instead of over a line. Okay. And it's a triple integral instead of a double integral. But other than these obvious changes, these obvious differences, it's morally the same exact theorem. Right? By the way, for morally equivalent reasons that you can think through on your own if you'd like. Again, check and make sure that both conditions satisfy. A symmetric domain by itself, not worth anything. It's not just that you might get the wrong answer, it's that the argument doesn't work. Right? So you can keep that in mind. Again, it's got to be the same plane for both of the symmetries that you're claiming. Again, otherwise the argument doesn't work. So my example here is this conjures a lot of memories for me, by the way, from undergraduate days. Doing integrals on a ball is pretty routine, right? This happens a lot. The world is full of balls, as it turns out. Right? So how am I going to compute this integral? Well, I guess we could slice it up, square roots everywhere. Okay, I guess I could do spherical coordinates. Well, yeah, pros and cons on that as well. But look how much easier this actually is. If I choose the XY plane, for which this is my reflection, right? If you're reflecting through the XY plane, the reflection just it just puts a minus sign on the Z coordinate. And this minus sign goes into there, a la this. And compute, and altogether the reflection indeed gives you that minus sign. This integral is 0 by a symmetry argument. And we don't have to do spherical coordinates, no rho squared sine phi, no trig, no square roots, nothing. Just a couple of clever observations, a little bit of algebra. Done. Everybody on board? Okay, now there is a tricky part to this that I just glossed over that I want to come back on and dwell on now. a reasonable question would be, where in the world did I come up with this? Why did I decide to look at the XY plane? Did I just get lucky? How are you going to decide when you face a problem along these lines? Something like that. Who knows? Something like that. How would you know? Should you try the XY plane? Why not the YZ plane? Why not the XZ plane? Why not Y equals Z? There's a lot of options here. Balls are symmetric through countless planes. Why the XY plane? Here was my reasoning. I know I need my integrand to be odd. I need this to be odd. There's an aspect of what I see here that screams oddness. And that is the odd exponent. After all, that's why they call them odd. Right? So my first thought when I look at this integral is, I sure would love it if this were my formula for my reflection. Wouldn't that be nice? Right? Wish list. If I could have my reflection just stick a minus sign on the z coordinate, that minus sign would get cubed and end up in the minus sign that I need to prove oddness. So this 3 motivates that I wish this could be my reflection. Everybody see my wish list there? Any questions about that? Now, this is a wish, right? I'm hoping. Wouldn't it be nice if this could be my reflection? But then I have to ask myself, is this a reflection at all? Or is this just made up, hopeful, wishful thinking? And if it is a reflection, what's it a reflection through? A little bit of geometry might persuade you, I hope, that this is a reflection through that plane. Right? So I reverse engineered my plane. Right? I start with what I have, and that made me want this, and that made me want to choose this. Then the reasoning we present goes in the other order. You don't have to show your wish list reasoning. You don't have to, you're strategizing. You're not responsible to show that. But having thought through this green, I can then make it look like I have an inner oracle that caused me to choose the XY plane, that caused me to write down this reflection, which then allowed me to prove oddness. Right? So the reasoning that we present goes backwards from the sort of the strategizing that we started with. What do you think? Everybody follow that? Oh, yes.
Does the logic work that if the double or triple integral is 0, that there has to be some line?
Sadly, no.
Does that?
Yeah, sadly, no. Now there's plenty of examples where that just doesn't work out. Yeah, tempting, but some integrals are just 0 for weird reasons, non-symmetric reasons. Was there another hand somewhere? Yeah.
Is there a way to draw it out to verify the logic, or
I'm not sure what you mean.
To draw out the way we reverse engineered it on a graph?
How my sort of the 3 led to this, which then led to this? Yeah. Well, yeah, I can just, at least I can draw this part, right? This part here, the 3 motivating this minus sign on the z, that's algebra. Right. That's sort of anticipating that, that cubed is going to give me the minus that I want, so I don't really have a picture on that. But looking at the purple part here, yeah, sure. Let's see if I can. I don't really have any space. I'll squeeze it in down here. Here, I'll zoom. Now I got a lot of space. Okay, so looking at. Whoops. There we go, XYZ system. And let's look at, so my reflection takes points into the XY plane and then, equal amount further to the other side. This turns XYZ into XY negative Z, right? And notice that the halfway point here, this halfway point is always in the XY plane, right? And you make the same argument for any other point, wherever it happens to be, XYZ turning into XY negative Z. In that transition, the halfway point is always in the XY plane. Is that satisfying?
Yeah, it's just I had a follow up. Like, wouldn't that only like be more feasible for like lower number exponents? Like, if you had a higher power or like more convoluted expressions, wouldn't it be harder to do this kind of tactic?
Maybe. Yeah, I'm not saying that this method works in all cases. Now that said, it's not how big this number is. If this was a 375,
Right.
That's cool. All that matters is that this number is odd, and then this whole argument works. So, yeah, it's not so much how big the exponent is, but obviously, if it's even, that's kind of a dead end. If it's a fraction, okay, that would make things weird, I guess. You'd have to think it through more carefully. But there's always limitations on every method. Totally. Yep.
So if you can just look at the function and try and plug something in, that would basically give you negative x, y, and z. From there, you can try and like ration what the planning would be.
That's exactly the point. Yeah, that's right. So think about wish list on what you see. And by the way, I'm not saying this is always the way to find your plane or your line or what have you. But this being an example of the case, sometimes looking at the algebra motivates what your reflection ought to be, and then what your reflection you want to be motivates what the plane is. Yep. All right. Okay, last thing in chapter 5. So we're done with 5.5 now, by the way. It took forever. I think it was at least, I've lost count. But anyway, it's been at least 3 lectures. It might have been 4. Finally done with 5.5. Moving on to 5.6. This is a mishmash of different things. I'm going to try to keep the focus as much as possible on the math. There are some physics applications of this. And more relevantly, there are some physics scenarios that motivate some of the math. So that said, I'm going to try to keep the physics to a minimum, because this is not a physics class or an engineering class. And the distinction that I make is that if you're doing a physics class or an engineering class, you can make physics or engineering arguments, and we'll see an example of that in a few minutes. Whereas in our course, I want to keep the arguments that you give to being mathematical arguments, not physics arguments. Okay, getting ahead of myself. Okay, we're going to start with this concept of a weighted average. And a weighted average, in fact, y'all have heard of this before, because this is how we're going to do course grades in this course. So if you weren't entirely sure what a weighted average is, this will clarify that. Starting with just an average, this is how you average numbers, right? Here I've got 6 numbers, and I've averaged them by adding them and dividing by 6. Now I'm rewriting that over here a little bit. Of course, the number of terms in the numerator has to equal to the number of ones in the denominator. That's where the 6 comes from. The 6 comes from the fact that there is, 6 numbers in the numerator. Okay. So now I'm going to kind of group these together. And then I'm going to rewrite those groups like this. And this is what we're going to call a weighted average, an expression that looks like this, which you'll notice I can rewrite like so. We're going to call these numbers here, like the 2 and this 1 and this 3. Those are the weights, what we call weights, because they indicate how many times are the various numbers being counted. 4 is being double counted in that average. Right? So we're going to say it has a weight of 2. 7 is being single counted, weight of 1. 8 is being triple counted, so it has a weight of 3. And so notice from the way we wrote it on the right there, the weights just go there. The numbers that you're averaging, the 4, the 7, and the 8 in this case, go there. Go there. And so here we have a sigma expression describing what we call a weighted average. Again, the idea being that the weights are motivated by sort of an indication of how many times does it count, double count, triple count, whatever. What do you think? Is everybody on board so far? Now, if you're going to take a point of view of something being literally counted a number of times, that's unavoidably an integer. right? You can't count something 2.5 times. It's not clear what that even means, right? But you can totally have these numbers here, these what we call weights. You can have those numbers be anything you want. They don't have to be integers. They're just how much impact in some sense. Get away from the idea of double or triple counting. It's not a counting thing, but just how much impact you want each of the values to have on whatever average you're computing. So, examples. This example here is very analogous to how this course works in terms of grades. Weighted averages. You'll notice that exams 1, 2, and 3 have weights 20, 20, and 20, just like in our class. This is not exactly like our class, though, because there's apparently a 4th exam, which has a weight of 40. We don't have that. So we have a final exam that counts as 30, and then the homework is 7, and the attendance is 3. Right? So different weights, but just to keep the numbers simple, I'm doing it like this. Okay, so Bob gets these grades right here. And Bob wants to know what grade he gets in the class, of course. So, okay. Well, the numbers that we want to average go right there, a la that part of the formula. The weights go right here for that part of the formula, the blue part of the formula. And there's our arithmetic. And all together, the course average for Bob here is just a little bit under 3.0. Now, how are we going to deal with stuff like this? This is not exactly a 3, right? But remember, the way I deal with this in this course is we have bins, right? And if I remember correctly, anything from 2.85 to 3.15, anything in that range is a B. So Bob, as a result of those exam grades, gets this average, which translates to B. Does that all make sense? There was a fair amount of up and down in Bob's performances here, right? I mean, Bob had a couple of good grades, and he got off to a rocky start there, but ended up doing pretty well on that last exam, worth 40% of the grades. So this was a big win for Bob right here. This business here, really big help. Probably brought him up from a B- to a B. Okay. All right. Is everybody happy with this example? All right. Okay, so let's talk about generalizing this to a continuum of numbers. And this is a harder idea if you think about it. If I ask what is the average value of a function, well, golly, if I draw a function f, let's say this is my function f. I'm drawing a graph, of course. Well, the values that f takes on all of these values between there and there. How am I going to average all these numbers? Do I just average the endpoints? Do I just take the point in the middle? Is this the average value of the function? No, that's not fair. Right? This function takes on, for example, values in this range between there and there. For a much greater fraction of the time than it takes on these values between there and there. Oh gosh, art challenge now. I think I already messed this up, but anyway, you can see much less often at these high values and much more often at these low values, right? So the size in the domain, right? For how many input values, in some sense, does the value of the function have this output value, this range of output values? Much more often with lower numbers than these higher numbers. So I don't just want the average of all these output values themselves. I mean, that doesn't even make sense, right? What we're going to do to account for how often this business in the domain is to do a weighted average weighted by size in the domain. So, size in the domain is the weights. So, dx, size in the domain. right? And then we're averaging the values of the function. So, these values out here, sure, that's what we're actually averaging, but weighted by size in the domain. You'll recognize then the rest of this as being the usual formula for a weighted average. It's a summation. Okay, it's an interval, but it's a summation, right? And everything else lines up. And this simplifies as a formula. This simplifies, very nicely. This denominator, of course, is just b minus a. So that's a nice little streamlining to keep in mind. So in practice, this is really the better formula to remember for the average value of a function. But I like to underscore that it comes from weighted averages. Okay. All right. So applying to looking at sine x on this interval here. Well, sine x goes from 0 to 1 and back down to 0. Is the average a half? Well, I feel like sine x, when it's low, it's increasing faster than when it's high. High values of sine x stay high. They're kind of flat up there. And so you'd think the function stays in the high range a little bit more than it does in the low range. So a half doesn't feel right. Computing from this formula here, 2 over pi, which is a little bit more than a half, as expected. Everybody happy? All right. Okay, we can do the same thing in multivariable. No big deal. This is the exact same idea. Two-dimensional domain. Size in a two-dimensional domain is area, not length. So double integral dA instead of single integral dx. And again, the denominator simplifies very nicely. And so again, this becomes a plug and chug. And so here we go. Let's look on the unit disk. And let's consider what is the average value of this function, x squared, on that unit disk. Okay, well, we take our formula. Here's our formula. And plug and chug. Now, this is just polar coordinates. You can compute that integral however you like. I think polar works out nicely. And here you go. Average value, 1/4. Oddly round number for a question that involves a disk, which, so you're thinking square roots and trig and possibly horrible answers, but nice, easy, nice round number, which is mysterious. What do you think? Everybody all right? Okay. All right, so to a little bit of physics then. What is center of mass? There's different ways to motivate center of mass. I like to think of it, now this is a math point of view, I like to think of it as a weighted average. It's a weighted average. It's a weighted average of position, right? Position is a way of describing a location. A center is a location. So it kind of makes sense that if you want to find a center of something, you're going to be looking at the positions of all the points involved, right? And center of mass, well, kind of believable that you'd want to take a weighted average of those positions. This is just, for intuition purposes. So taking this as a given, weighted average of position, here you go. For example, if you have 2 points, there is the weighted average of position. After all, the positions, x1 and x2, are what I'm doing the weighted average of. The weights, aka the masses, are m1 and m2. We do with them what we do with weights. Put them there. And there's your formula. Okay, now, it's just a formula. Let's talk real quick about the physics intuition behind this, and I'm going to leave the details for y'all to check if you're curious. And again, physics is not our goal here, right? But if you were to have these masses at these positions, and if you were to connect them by a thin, weightless, sort of like support rod in between them, something like that, this thing is what we call the balance point, as it turns out. That's where you would put your finger here so that this, kind of weird offset barbell looking thing would balance. So the torque of the first mass pulling down on the left and the torque of the second mass pulling down on the right, those torques would balance perfectly. So different point of view on the center of mass, if you prefer. And again, you can make an argument. You can literally write down the torques. Again, physics. This is not what we're doing here. But if you know what torque is, and if you write down the torques at this point by these two masses, and set that torque equal to 0, you'll find this for X bar. Okay. Alrighty. So general construction. Now here we had just two pieces of mass, so we only had two terms in the summations. In general, arbitrary number of points. In other words, mass distributed over a region, not just a discrete pair of masses. Then we get this formula right here. Again, weighted average, weighted by the masses, highly analogous. And again, the denominator simplifies. Now, there is another thing I should say. What I've got written down here, I have to confess, I have not technically actually defined this. An integral of a vector-valued function. Right? We haven't defined that. What is that? Here's the good news. It's actually a pretty easy idea. When you do an integral, you're just adding and multiplying by scalars, all of which is done one coordinate at a time. And so this is nothing more than a vector whose coordinates are what you get when you integrate one coordinate at a time. So do this integral for x1 through xn, make a vector out of it. Okay. All right. Okay, example. Suppose you have this upper half disk. Density equals 1, just to keep the algebra simple. So uniform density disk, radius A. Let's find the location of the x coordinate of the center of mass. From the formula that we just looked at, here's this is how we're going to compute that x bar. And this integral is equal to 0 by symmetry. Don't forget to check the details. I think this is a nice little practice problem. Right? Make sure you remember when I say details here, so you've got to give me 5 details. What is the line over which we're making a symmetry argument, et cetera, et cetera. Right? And I think you'll find that this argument works just fine. So, nice observation. By the way, this is a great example of how symmetry arguments come up. They come up unexpectedly. They come up when you're doing something else. You're looking at a physics problem or an engineering problem or whatever, and it just happens to be that oh my gosh, what are the odds? And that integral actually satisfies all your requirements, and you can just just declare it to be 0. So comes up a lot. Again, 20% of my undergraduate physics major, I think, was 0 by symmetry, a la this example. Okay, now I emphasize here, I do want you to give me the math symmetry argument. That's about lines and reflections and oddness, etc. Right? I need a math argument. This is a math class. There is, however, a physics argument. This is not appropriate in this class, in my opinion. And the physics argument would be to say, all right, well, look, let's just imagine, just use your physics intuition. If you had a uniform density half disk like this, and if you kind of supported it by your arm and tried to balance, it's going to balance. Right? The torque on the left, the torque on the right are the same torques. It should balance. That means the center of mass has got to be on this line. That means the center of mass's x coordinate would be 0. Right? So this balancing torques argument is a perfectly valid physics argument. Not okay in the math class. I need the math argument. Does everybody see the distinction? I hope. Anybody any questions about that distinction? All right. Okay, let's see here. Real quick, I just want to wave my hands at the y calculation. Here's the appropriate integral. You can turn it into either one of these iterated integrals and compute. Sadly, no symmetry argument. You do have to crank one of these out. You get to pick which one of these you want to crank. There is a temptation to choose this one because you look at that right there and you think, oh, I love it when my integrand is a constant, right? An x antiderivative of y. Y is a constant. And it's tempting to say, oh, that's the easiest first step. I don't know, for lack of a better idea, let's just go with whichever approach gives me the easiest first step. But look at this other one here. Now here I don't have quite as easy of a first step, but something really beautiful happens, and you can be on the lookout for this. This has come up many times, in my ye old days of when I was a physics major. This y, you take the y antiderivative, it gives you a y squared, and when you plug in this scary algebra of a square root into the y squared, the square root goes away. So, arguably an uglier anti-partial, but better because it makes the square root disappear, and that makes your outside integral way easier than the first option. So I strongly advise, and this is always a good thing to be on the lookout for, look for opportunities like this where this and that kind of, that's a happy coincidence right there. Be on the lookout for that. This is one of many little bits of good fortune that you can come across that'll make this a much more desirable way to go compared to this relatively, not so good way to go. Everybody all right? Okay, sorry to go over drawing a line right there. We'll pick up here on Wednesday. Have a good day. Welcome back. Good to see y'all. And as usual, stick around if I didn't get your attendance.